Hello, everyone. Thank you for the introduction. In this presentation, we will discuss the development of bio-based vitrimer composites for wind turbine blades, providing some context and an overview of the work being carried out within the EOLIAN project. Since I will be sharing this presentation with my colleagues from Politecnico di Milano, our goal is to give an overview of the synthesis of the material, as well as the preparation and characterization of these composites. As it has been commented previously, the context of the project is that the wine blade manufacturing sector is shifting toward more sustainable materials driven by the need to reduce environmental impact while maintaining a structural performance. Growing regulations and the move toward a circular economy are intensifying the demand for alternatives to traditional thermoset composites. To introduce the concept of vitrimers, we first need to look at the two traditional families of polymers, thermoplastics and thermosets. They are mainly differentiated by how they respond to heat. Thermoplastics consist of long linear and branched chains held together by relatively weak interactions. Because of this, they soften and melt when heated, and they can be reshaped over and over without major chemical changes. This makes them, at least in principle, melt recyclable and suitable for processes like injection molding, extrusion, or whatever. Thermosets, on the other hand, behave very differently. During cooling, they form irreversible three-dimensional cross-link networks. Once this network is formed, they no longer melt, and if we heat them again, they simply degrade instead of flowing. This gives thermoset excellent heat resistance and dimensional stability, but it also means they are very difficult to recycle. This brings us to the concept of adaptable covalent networks, or CANs. In summary, CANs bridge the gap between thermoplastics and thermoset, offering the stability of a thermoset with the reprocessability of thermoplastics, and thanks to the adaptable covalent networks. So CANs are polymer networks with covalent crosslinks that become dynamically reversible when exposed to a specific stimuli, such as heat, catalyst, light, pH, among others. In the absence of a stimulus, their cross-link structure gives them thermoset-like properties, including high strength and durability. And unlike the traditional thermosets, CANs can be recycled, reshaped, or repaired thanks to this dynamic nature of the crosslinks. So dynamic polymer networks can be classified in two main types, depending on their interaction mechanism, dissociative CANs and associative ones. In a dissociative CAN, the covalent bonds break before the new ones form. This leads to a temporary loss of network integrity, causing the material to behave more like a viscous liquid when the exchange is activated. In contrast, associative CANs follow an exchange mechanism where a new bond forms at the same time that the old ones breaks. This means that the material keeps a constant cross-link density, preserving its network structure even during bond exchange. Vitrimers belong to this second category, the associative CANs. And because their network remains intact while the bonds rearrange, they combine the stability of thermosets with the ability to flow when heated. And this unique mechanism gives the vitrimer several key advantages, such as tunable properties depending on the chemistry used, self-healing capabilities, reprocessability, meaning that they can be reshaped, recyclability, and the shape memory behavior. Altogether, vitrimers represent a new generation of adaptable materials that bridge the gap between thermoplastics and thermosets. So vitrimers can be synthesized through different routes, depending on the type of dynamic bond used. In many cases, a catalyst is needed to activate the dynamic covalent exchange, while other chemistries can operate without one. In this slide is summarized the main dynamic chemistries available for designing these vitrimer networks. And within the EOLIAN project, we focus specifically on amine and disulfide chemistries. So in the EOLIAN project, we explore the development of a range of sustainable epoxy vitrimers based on amine bond. And for this purpose, in the first step, we are working on the synthesis of a sheep base as a dynamic hardener. Sheaf bases are typically formed through a condensation reaction between a primary amine and an aldehyde, producing an amine bond as this key functional group. Traditionally, this reaction relies on petrochemical derived aldehydes obtained, however, more sustainable alternatives can be employed. In our case, we are using vanillin, which is a bio-based aromatic aldehyde, obtained from, for example, lignin or other renewable sources, and can effectively replace conventional aldehydes in the synthesis of these sheaf bases. We can obtain this hardener as a powder in this example with a high melting temperature. In the second step, the hardener is reacted with an epoxy compound to obtain the vitrimer. In this case, epoxy resins derived from oils, such as linseed oil, has been selected as a renewable source. Once we have the vitrimer, in this slide we present some of the key results obtained until the moment for the amine-based vitrimers developed within the EOLIAN project. On the left, you can see that some of the developed materials achieve a bio-based content of over 60%, demonstrating our progress toward sustainable formulations. The vitrimers also exhibit mechanical and thermal properties in accordance to common epoxyamine thermosets with aliphatic structures. We are still working on achieve the requirements for the wine blade application. But also we have confirmed the processability and repairability as shown in images where the materials were reshaped or healed after damage. Additionally, the materials show good solubility, which is very beneficial for recyclability. But we have to say that we still are facing some challenges as the viscosity, for example, which remains an issue for processing. To address this, we have different strategies that we are working on. For example, we are investigating vanillin-based diamines with different chemical structures, as well as the incorporation of reactive epoxy and phenolic diluents. And also we are adjusting the starting material structures and incorporating diverse epoxy system to further optimize the material properties. Overall, these results demonstrate both the potential of the bio-based vitrimers and the ongoing strategies to improve their performance. But due to the challenges associated with the amine chemistry, alternative approaches are currently also being explored. One of these alternatives is the development of vitrimers with disulfide bonds. In this context, various covalent hardeners are being investigated, such as cysteamine or EAFD, to enhance the properties and the performance of the materials. These alternatives can be easily available, easy processing, and in some cases more affordable, and also can be potentially bio-based precursors. So in this sense, first trials have shown better, good viscosity values and mechanical and thermal properties that could fit well with the requirements and some of the properties associated to vitrimers. But we are still on the characterization and development of all these materials. Well, I think it's all from my side, and I hand it over to my colleagues from Polimi to continue with the presentation.